Okay, let's consider the function y equals the backward apostrophe c backward apostrophe plus 1 plus backward apostrophe a over 10 raised to the x. Okay, backward apostrophe a or c in your case is d-u-b-a-v-a-y 8. And a is 5. Okay, so we have y equals 8 times 1.5 raised to the x. Now, the instruction that you would have is graph I'd say graph on semi-log because we used to graph on semi-log paper starting in high school because we use logs a lot to do our calculations. Now a lot of that is bypassed, but I say graph as a semi-log graph. And find the equation of the graph. Okay? Well, that means basically you could have a XY table. The semi-log table. So here's your function. Semi-log, to put this in the could be natural log of y versus x. Could be any log. It wouldn't matter. But we'll do natural log. Excuse me. So we could do this with a number of values of x. Okay, we could evaluate this. You know, for example, if x is 2, then y is going to be 20. Okay? If x is 3, then y is going to be, turns out 30. If x is 4, it's going to be 45 and so forth. I think those numbers might be accurate. So we can make a table and we could do the natural log of y and we could plot the points. Okay? We're not actually going to do that, but when we have data, that's how we're going to approach the data, and we'll do examples of that shortly. And we've done a couple, but let's make sure we understand the terminology. I think if you're having any trouble with this, it's simply a matter of terminology. I don't think you're going to have any trouble with the mathematics. I think you understand it. Okay, now, what we do then is we find the equation for the natural log of y. Okay, so y equals 8 times 1.5 raised to the x. So the natural log of y is the natural log of 8 plus natural log of 1.5 to the x. Because the natural log of the product of 8 and 1.5 to the x is a natural log of 8 plus the natural log of 1.5 to the x. And you're fine with those calculations. Well, that equals the natural log of 1.5 to the x. Another law with which you're perfectly familiar is that that's going to be x times the natural log of 1.5. Now, just to make sure we really understand what this is telling you, this is then natural log of 1.5 times x plus the natural log of 8. Well, this is mx plus b, where m equals the natural log of 1.5 and b equals the natural log of 8. Okay? Now the natural log of 1.5 is probably 0.4 something. So I'm going to say that's approximately, I'm going to guess 0.42 plus, that's going to be about 3.1 maybe. It's maybe something like 0.42x plus 3.1. Okay, and of course you use your calculator, you can get more accurate numbers there. But assuming that those numbers are reasonably close, and I think they are, but I'm never surprised when they aren't. Okay, this means that your graph of natural log of y versus x will have a y-intercept of 3.1 and a slope of 0.42. And if you wanted to graph that, you know, when x is 1, well then you'd add 4.2 to 3.1, you get 3.52, so you'd have the point. Okay, and you'd have the point 2, 3.94, and so forth. Okay, so that's what the graph would look like on semi-log paper. If you plotted, you know, if you calculated the y values for x equals 1 and 2 and put them on the table here by taking the natural logs, okay, those are the numbers you would get on this table. More or less, you know, to the extent that my estimates are accurate here. So there we have what you do if you're given a function and asked to put it on a semi-log graph. Now let's suppose that we have a graph where 1 is here on this axis and 1 is here in this axis, and this is natural log of y versus x. And let's say that the graph is this. Okay, so this is a straight line graph, meaning that natural log of y is like mx plus b, where m is the slope of this line and b is the y-intercept. Well, b it's not actually the y-intercept, It's the natural log of y-intercept, so maybe I'd better write it that way. But you can see that b, as I've drawn it, appears to me to be about 1.9. So m equals what? Well, I would say that if this is 1.9 here, let's just estimate the x-coordinate of the x-intercept. There's 1, there's 2, there's 3, there's 4. And I like to use fundamental triangles. Looking for a better color, but I'll use this. So I'm going to use the fundamental triangle for these 2 points. And say that the rise is negative 1.9 and the run is 1, 2, 3, 4, 3.7 or 3.8. Actually, let me fudge and use 3.8 because I was debating about that. Gives us a convenient value for the slope. So m equals negative 0.5. Thus, the natural log of y equals negative 0.5x plus 1.9. So y equals e to the negative 0.5x plus 1.9. And again, that's a step. Once we have natural log of y, I think you're pretty much home free. We can easily see what this is going to be. So that's e to the negative 0.5x times e to the 1.9. And e to the 1.9 is somewhat less than 7. I'll say maybe 6.8. And that's really, yeah. And you know what? It reminds you, over here, I made an ignorant estimate. That 3.1 should have been a 2.1. So that should be 2.1. And I'm not going to make the correction here, but that should have been a 2.1. And all these 3's here should have been 2's. Okay, well, back to this. Okay, we're not getting 6 point something. Yes, we are. We're getting something about 6.8 maybe. And I'm not very careful about that 8. I could be off by a couple of tenths very easily, and even worse. And e to the negative 0.5, e to the 0.5 is a little less than 1.7. So the reciprocal of that would be a little more than 0.7. So I'm just going to say 6.8 times 0.7 to the x and that's a reasonable approximation to the function. So that what you see here is once we have the line, once we have the graph of the line, and hang on, I got something sticking to the bottom of my foot there. I don't know why. One of my cloths. Not sure I want to know why. Anyhow, so once we have the equation of this line, we just do what we know how to do. We exponentiate both sides and simplify, and we get our basic exponential, or our approximate exponential function. Okay, so these are two fundamental ideas that give us most of the insights we need in order to linearize exponential data and obtain exponential models and understand what it is that we're doing in the process.